Hi OpenXML developers, this is Eric White. This is the next screencast in a series of screencasts on writing recursive pure functional transformations. And in this screencast and the previous two screencasts, we've been covering the semantics of linked XML. We've been covering those semantics that are necessary in order to write these types of transformations. In the first of the linked XML screencasts, we covered functional construction. In the second one, we covered namespaces and XName objects. And finally, in this one, we're going to cover the linked XML axes. So what are axes and why are they called axes? In geometry, an axis is a line that intersects through a globe or through a circle or something like that. And the analogy in XML is that an axis is a way to slice and dice your XML tree. For what it's worth, this is the same nomenclature that is used in XPath expressions. So here's a simulated XML tree. The most common axis method is the elements axis method. So if you take this E2 method and ask for its elements, you're going to get E21, E22, and E23. These are the child elements. If you pass an XName to the elements axis method, then it will return only those elements that match that XName. One note about this is that when you pass an XName to one of these axis methods, it's actually very, very efficient. In the previous screencast, I mentioned this point about XNames being atomized. So when you pass E22 to the elements axis method, that E22 is converted to an XName object, and that XName object is in fact the same XName object in the XElement that represents that node in the tree. So therefore, the elements axis method needs to only compare whether those objects are equivalent, and it gets extremely fast performance. It's effectively only comparing two pointers to see if they have the same value. There are a number of axis methods in linked XML that take an XName object. These are all the axis methods that return only elements or return only attributes. And that makes sense. Only elements and attributes have names. Here is the linked XML program that creates the XML tree that we saw in that Visio diagram. And if we run this program, we see the results. And here we can see all of those elements in that tree. Now I'm going to change this code. So here I'm going to use the Descendants axis method. I'm going to pass that E22 XName into that axis method. That returns a collection of all of the elements that have that particular XName. And then I use this first or default method to get just the first in that sequence. And so this will return the one and only E22 element in that entire tree. And then, if I want to, I can iterate through all the items in that result, and if I run it, we'll see those child elements that we expected to see. And as you saw, I can pass the E222 XName into that elements method and we'll get a single element back. The attributes axis method works in an identical fashion. To demonstrate the attributes axis method, I'm going to add a few attributes to this tree. So now I've added 3 attributes to the root element. Now remember, attributes cannot be repeated within a particular element. You can't have 2 attributes with the same qualified name in one element. And if I run this example, we do see the root element up there at the top, and it has those 3 attributes. So now I've changed the query to return the set of attributes for that root element, and then the code iterates through those results and prints each item in those results. And we see the 3 attributes. Now I'm going to put in att1 in there. And of course it returns that single attribute, as you would expect. But a key point about this is that because attributes can't have repeated names, when you pass in a name to the attributes access method, you're only going to get a single attribute back. So you might as well, in this circumstance, just call the attribute method and print out the result. And you get the same result. However, there are times that we do want to use an attributes access method and pass in a name to that attributes access method. And this happens when we are using the extension attributes access methods. And I'm going to talk about that in just a minute. But before we talk about extension methods, I'm going to just iterate through all of the other access methods. Back to our diagram, if I find the E2 element and then find all of its descendants, we're going to find in document order all of these elements. So now I've modified this query to first find the E2 element, and then it uses the Descendants access method to find all of the descendants of that E2 element and prints out the name of each one of those elements in the result. And we see exactly what we expect to see from that diagram. There's another access method, which is you can just add and self to that name, and the only difference is we get the E2 at the top of the list. One point I'm going to make about this line of code here, this code that finds the descendants and then passes the E2 XName to that method and then gets first or default. You might think that this would iterate through every single item in the tree, and in fact it doesn't. What it does do is, in this particular case, it would first go to the E1 element. It would go through all of those descendant elements of E1 looking for that E2 element. After it looked through all the descendants of E1, it would go back up to the root, and then it would go to the E2 element, and it would find that element, and then the first or default method that we can see here, that would actually short circuit the query and stop the query at that point in time. That first or default method will take advantage of the laziness of the Descendants access method. Remember, we talked about laziness and eagerness in a screencast quite a bit earlier in this series, and it will stop that query. Now, one thing that we could do is we could change this to elements of E2, and we get the exact same result. And another way to write this is we could just change this to element E2, and we'll get the same results. This would be the most efficient way to write the code, but one point about this is elements of E2 dot first or default. This is very, very nearly as efficient as just calling the element method and passing E2 to that element method. And as long as we're talking about the elements method, a couple of other methods that are interesting are the elements after self and the elements before self. And these return the sibling elements. So if you take this E21 element as your starting element and you ask for elements after self, the results of that query will contain 2 elements, and it will be E22 and E23. If you take E23 and ask for elements before self, it returns E21 and E22, but a key point is it returns them in document order. So it'll be E21 first and E22 next. And the reason for this is that the LINQ to XML API internally uses a singly linked list. There is a link from E21 to E22, but there is no link from E22 back to E21 in the .NET implementation of LINQ to XML. So that means that if you use elements before self, let's say that you're on the E23 element and you want to find the element immediately preceding it, and you ask for elements before self, and then you take the last one, this is going to be a very slow process. This is not going to perform well, because if you have, for instance, 50 elements and you want to iterate through all of those elements and maybe filter each element based on the element immediately preceding it, then it's going to go fast for the first one. It'll go elements before self and it won't have any. Then the second one will find the first one. And then the third one, it'll find the first and second one. And then the fourth one, it'll find the first, second, and third. It's actually an operation of O of n squared. If you have 1,000 elements in there, it will take on the order of 50 or 100,000 operations to find the previous element for all of those elements. But there's a solution to this. Some time ago, actually back in 2009, I wrote a little bit of code that enables you to do elements before self in reverse document order with good performance. And what it does is this code goes through and annotates every node with the previous node. When you first call nodes before self in reverse document order, it notices that those annotations are not there, and then it takes the time to go and put those annotations on every node. And from that point on, you can call these methods nodes before self fast and elements before self fast, and that will return those nodes with very good performance. You can find this blog post at this location. One interesting point about this is that in the LTXML.js implementation, in other words, this linked XML implementation for JavaScript, I implemented it such that elements before self, reverse document order, has the same performance profile as elements after self. So this means you can call elements before self, reverse document order, get first or default, and that performs really well in the linked XML implementation for JavaScript. Up till now, we've only been talking about elements and attributes, but there are times when you have to also deal with other types of nodes. Specifically, you might need to deal with text nodes, comments, or CData nodes. So let's modify our little example here. First of all, I'm going to get rid of our 3 calls to X attribute. We don't need those anymore. And now I am going to add a new xText node to this first element, and I'll put ABC in there. And then following that, I'll put a new xComment. And now I'm going to come down here. I'm going to find the E1 element, and then I'm going to get the descendant nodes for that E1 element. And instead of writing the name, I am going to write the node type. I don't want to print the whole node, because if I printed the whole node, then for every element in the result set, I'd get the entire tree from that node all the way down to the bottom of the tree. It would be too much output. I don't want to print the name because comments and text nodes don't have names. So if I just print the node type, we'll get an idea of the result set. And if I run it, we can see that we get element, element, text, comment, and then a whole bunch of elements all the way down, as we expected. There's also the similar descendants nodes and self axis method, and there are also nodes before self and nodes after self axis methods. The last thing to talk about are the extension axis methods. So what the extension axis methods do is that you first call one of the axis methods on some element, say, and then you can then dot into an extensions axis method, and it will call that axis method for every element in the first result and give you the combined results of getting all of the child elements of each element in the first node. That might sound a little complicated. Let me show you exactly what it means. I'll clear out the nodes. We don't need them anymore. I am going to query. I'm going to take the root node. I'm going to dot into the elements method. If we go back to our diagram, if I started this root node and get the elements of that root node, it's going to return E1, E2, and E3. I'm then going to dot into the elements method again, and that is going to use the extension method and return all of the child elements for all the elements in the first result. And so that's going to return basically this entire slice of elements all the way across the screen, all the elements that are 2 levels down. So I've taken root, I've dotted into the elements axis method, and now I'm dotting into the elements extension axis method. And now I'm going to print out the name for this particular query because every item is an element and every element has a name. So what we're going to see is this prints out E11, E12, E13, E21, E22, E23, and so on. There are times when this idiom is extremely powerful. It's really what you need to use. Another example of using an extension axis method is if we want to find all of the attributes of a given name throughout the entire tree. So let's say that here we have a new X attribute. And down here we have a new X attribute. And somewhere down here we have one more. I'm going to print out the entire tree, and we can see our attribute up here under the E11 element, under the E13 element, and all the way down at the E33 element. So now I can use the attributes extension axis method. I first get every descendant in the tree, and then I call into the attributes axis method, and then I will iterate through the results and print each item in the result. Let's run the program, and in fact it did exactly what we wanted it to do. It found all of those attributes through the entire tree, and interestingly enough, it actually did it in a pretty effective way. It is efficient to get all of the attributes like this in the tree. And it's great that we can do an operation such as that in such a small amount of code. I'm going to show one more idiom with regards to these extension axis methods. Let's examine this example in detail. This example contains some pseudo OpenXML markup. Just to show you what the markup looks like, I'm going to print out root and put the program there and run it. And we can see here we have a root element. Underneath there we have 3 different paragraph elements. For each paragraph, there may or may not be a paragraph properties element, this PPR element, and that paragraph properties element has an attribute style, and that style is set to heading 1 for 2 of the paragraphs, and then that paragraph in the middle doesn't have paragraph properties. Now let's say that we want to go through and get the text for those heading 1 paragraphs. We could write code to get the set of paragraphs, and then we could go look inside each one of those paragraph elements and look for the PPR element, and if the PPR element is there, then we could get the style attribute and look for the value we're looking for. And the easier and more robust way to do this is to use the attributes extension method. So let's look at this query here. The query first takes the root element and it gets all the child elements with the name of P. It then filters all of those child elements. It filters them by this expression right here. And let's look at this expression. First of all, we take the paragraph and we dot into the elements method on that paragraph. And that's either going to return a collection with one element in it, or it's going to return a collection with 0 elements in it. There's only ever one PPR element underneath the paragraph property, but we don't really care. What we're interested in is calling this elements method so it returns either a collection of one element or a collection of 0 elements. In other words, an empty collection. We then dot into the attributes method, and so if the elements method returned a collection of 1, then dotting into that attributes extension method will then call the attributes method for each one of those elements and return the attributes that match that particular XName of style. And that attributes extension method is then going to return either a collection of 0 attributes or it's going to return a collection of 1. And then we call first or default. And the first or default method is either going to return that one style attribute or it's going to return null because that's what the first or default method does. If you call first or default, and if the collection has one or more items in it, then it will return the first in the collection. And if the collection is empty, it returns null. That's the semantics of that first or default method. So now we have either null or we have a single X attribute. We then cast that X attribute to string, and so null casted to string is null, and an X attribute that is there casted to string returns the value of that X attribute. That's the definition of casting in LINQ to XML, is that if you cast an X attribute to a scalar value, if the value that you're casting is null, it returns null. If the value that you're casting is a valid attribute, then it actually returns the contents of that attribute. So it returns heading 1 in the case of these two paragraphs that have heading 1 in it. So if we look at the first 2 lines of this query, then we have a query that returns a collection of paragraphs that only have a child PPR element, that only have an attribute of style that has a value of heading 1. We can then dot into the select method. This is the projection method, and that projection method we're going to dot into the run element, dot into the T element or the text element and get its value and return that value. And so what this is going to do is this is going to print first paragraph and third paragraph. And that's exactly what we get. So we wrote this query. It's 3 lines of code. It's a little bit dense, but once you get used to reading this idiom, it becomes very easy. You become very accustomed to reading this particular idiom. And we are able to, in a very small amount of code, to get all the text of all the paragraphs that have a style of heading 1. So this is another idiom of the extension methods that is very, very valuable. We'll be using that idiom when we write our recursive pure functional transform. I suggest that what you do is type in this program and play around with it and see how dotting into the elements method returns a particular collection, and then dotting into the attributes extension method returns a different collection. And then get familiar with the first or default method and how that first or default method will short circuit the entire query, and then how casting an attribute to a string gets the value out of that attribute. Finally, we're going to take a look at the JavaScript implementation of LINQ to XML for 1 second. Here's the equivalent JavaScript example that uses the LINQ to XML implementation for JavaScript. First point is, all of the code to create the XML tree is exactly identical to the C# code. No difference there. Down here in our query, first thing is you'll see that this elements method uses the lowercase e instead of the uppercase e. We've seen that before because this is the convention that is appropriate for JavaScript. You don't want to use uppercase names for methods that you don't use new with. And then it dots into the where method. And in this where method, we can see over here that after calling p.elements and getting an enumerable back from calling p.elements, we have to wrap that into something called an XEnumerable. Then that has the attributes extension method. So then we can dot into the .attributes method, passing in style, and then we can dot into first or default. There's then another change in JavaScript. Whereas in C# you can then cast that X attribute to a string, the problem is in JavaScript we don't have the ability to write a cast operator overload. I mean, JavaScript almost has no types, so casting doesn't make sense. So I created a little method, lt_xml.cast. Let's go look at it. Here is that lt_xml.cast method. The argument is an element or attribute. If the element or attribute is falsy in the nomenclature of JavaScript, then it returns null. Otherwise, it returns the element or attribute .value. So this effectively accomplishes the exact same thing as doing that cast to a string that we did in C#. Following that, it dots into the select method, and that is a straightforward conversion from the C# code to the JavaScript code. And then this for each method down here, this is the idiom that you use in JavaScript as opposed to using the for each keyword that you use in C#. The big changes are here where we have to use this new XEnumerable, and also where we have to use this cast method to get the value out. Using those two changes to this idiom, we have the exact same logic in this example that we had in the C# example. So if we run this example, we see the same results that we saw in our C# example. So that was a lot to cover in one screencast. I don't know if you're tired, but I'm a little bit tired after going through all of that. Now, at this point in time, we have covered all of the prerequisite material that we need to cover in order to start talking about recursive pure functional transforms. So in the next screencast, we're going to talk about recursive pure functional transforms, and we're going to discuss the identity transform. See you then.